Okay, so this week and last week we've done our practice assessment for our Cartesian planes, and for it you were given a set of science results where the temperature of tap water was compared to the temperature of salt water when cooled by a chemical reaction. Our coordinates will be these values here. But before we can write our coordinates, we need to determine which is going to be our x values and what are going to be our y values. So we need to determine what our independent and dependent variables are. Now, just a general rule of thumb, your dependent variable, or independent variable I should say, is almost always going to be time. If time is present, it's going to be time. And the reason for that is we can't do anything with time. We can't go backwards, we can't speed it up, so it stays constant and it will always be our x value. Temperature in this instance is changing as the time progresses. So the chemical reaction is kept the same, the amounts of substances are kept the same, amount of water was kept the same. Our control variables have been kept the same essentially, but what we're measuring is the change in temperature as time progresses and then comparing the salt water to the tap water. Now to write our coordinates, all we had to do was to take the top value, time. So we've essentially got time here and temp. So we're representing our values as coordinates, and this makes it easier to plot them on the next page where we have to graph it. So if you look, we've got all of them listed here. You should have 10 because it was measured for 10 minutes. The next step, or the next question, was to graph your results. And because we were putting two different graphs on the same page, we needed to use a key. So what I've done is I've used green for the salt water and blue for the tap water. Really important things to note when you're drawing a graph. Firstly, we've got our title, we've got our units, our label, so telling us what we're actually measuring, and for linear and Cartesian planes, we need to make sure our numbers fall on the lines, not between the lines. And this allows for greater accuracy later on. If you just draw a 14 in the middle here, where exactly is 14? We have to sort of fix it to a place. Now you'll also notice that I've gone to 15 because we start with 15, but put the arrow after. The arrowhead needs to be included because it indicates that numbers continue. It's just that we don't have data values that are above 15 for this one. And you'll see I've done the same thing for time. I've put the label down the bottom, the units and the numbers are fixed to the lines. Now, in my key, I've got the crosses as being the saltwater plots, and I've also added my line of best fit here. Our line of best fit, we'll deal with it in just a moment, but it's the line that best fits the results that you have. It doesn't have to pass through any of the points. It just needs to be an average as such. Then I've got my tap water in blue doing the same thing. The crosses represent the actual data points and the line of best fit is the line in blue. You'll also see that there are dashed lines here, and that'll come up when we answer the following questions. So we'll come back to those as such. Okay, so for this you needed to research what a line of best fit was. And with that in mind, we have asked you to look for 3. Now, obviously, there are a lot of different sources that you could go with in terms of what you researched, and that means there are multiple answers for this section. But the thing that you need to remember whenever researching is to consider the reliability of your source. So, for example, you wouldn't ask McDonald's about what is a healthy diet because they have an invested interest in making you eat unhealthy food. So you need to make sure that the website that you get your information from for line of best fit or anything really has to be a credible source. So government agencies that have taken measurements, websites that are maths related for this would be a really good one. And you can often find that information down the bottom. You then needed to write it in your own words. So I've written my own definition. Yours will be different, and that's okay, but there's some key pieces of information that we need to have here. For our purposes, our line of best fit is going to be a straight line. Using a ruler, and using a clear ruler helps you make sure that you've got roughly the same number of points above and below the line. It's sort of an average and gives us a general idea of what the relationship between two variables is. It's not perfect. We need to remember that. So everybody's going to have slightly different lines of best fit, and that's okay. When you're drawing it using a calculator, obviously it makes it more accurate than doing it by hand, but really importantly, it doesn't have to pass through any points at all. In fact, if it doesn't pass through any, that's just fine. So we'll go back up and have a look at the lines of best fit that I've drawn. And you'll notice that I've got 1, 2, 3, 4, almost 5 lines above, points above. And then I've got 1, 2, 3, 4. This one here is an odd one. It's very, very low. And so it's perhaps an error. And in later years, you'll start to learn how to identify them and call them outliers. So it changes it a little bit, but it means that, you know, obviously the distance here is going to be quite great. Our blue line fits a little bit better, and that the results are a little bit closer together. And you could say that maybe the measurements in that instance were taken with more care. We then, using our line of best fit, need to find what the temperature is at time 3.5. So if we go back up, you'll see that I've added a dotted line at 3.5 and gone up to both of my lines of best fit. And I've used those to measure what temperature tap water was at 3.5 minutes and what temperature the salt water was at 3.5 minutes. And obviously it's not perfect, but I've said that it's 10.5 and that it is 11.6 for my salt water, and put it into the answers here, as well as putting them as coordinates. Well, it says at what time does the temperature reach 5 degrees. For the salt water, it reaches 5 degrees at 9.9 minutes. And for the tap water, it reaches 2 degrees at 9.4 minutes. Using our graph, our line of best fit, so it says use your line of best fit to fill in the data points. We go back up and we just trace the lines at, so at t equals 0, what temperature did the salt water and the tap water have? It was 15. At 1 minute, what did they have? 2 minutes, 3 minutes, 4 minutes, and 5 minutes. You fill those values into your table of values here. And then we can look at those graphs and sort of make it and describe what's happening. And it appears that salt water takes longer to cool down than tap water. For our last question, it is a challenge question, so it is supposed to be hard and it is supposed to challenge you, but you can still get some marks. So for example here, to find the constant, we're trying to find the rules for the graphs, essentially the lines of best fit that we have. They both cross at 15, so by just putting 15 in, you've gotten a mark each for each of those. So you could get 2 marks without even working out what the gradient is. To find the gradient, we remember that it is m equals rise over run, where m equals the gradient. We use m for gradient because it's not really used for anything else, whereas g can represent grams or gravity. We use m for gradient. So it's represented by rise over run. And all that's saying is how much do we go up or down divided by how much we go across, making little steps. Now you can do it this way by doing a little bit of a drawing and showing how much we've gone down. So we go 15, take away 1.4 gives us 13.6, or you could go 15, take away 13.6 gives us 1.4. So we've gone down 1.4 and we've gone across 1 because the difference between 0 and 1 is 1. We put it into our formula and we get negative 1.5. The other one, it's negative 1 on 1. We go down 1 and across 1, and it gives us a gradient of negative 1. You'll notice that I've not written in the number 1 here because we don't do it because it could look like a letter L. And in algebra, we need to make sure that our numbers are very clearly different from our letters. Another way of finding the gradient that you might have done in class is using the table to do so. So you're working out the differences here. So for time, or our rise, because it's our x value, sorry, our run, it goes up by 1. So each step is 1. Our rise is minus 1.4, minus 1.4, etc. So it gives us our rise, negative 1.4, over our run, which is 1. For this one, it's even easier because it's going down by 1 each time. And this is going up by 1 each time. So you end up with 1, negative 1 on 1. Rise, run.